you? Good?
How are you?
Good. So we are taking a break from R a little bit, and we're going back to talk about statistics, but then Lauren is coming back after me to do more R. So we're kind of changing things a little bit. So yesterday we talked about the experimental design and the ways of framing the questions, starting from the actual biological scientific question and translating this into a statistical question, and also talking about the experimental design. So today what I would like to do is to talk more about what happens once we collect the data, once we actually need to do the data analysis. Just to remind you why we're doing that, because the goal of our work is to do reproducible research in the sense that if we are to repeat our experiments, we should be able to obtain qualitatively similar conclusions. And for that, what is important is to provide ways to arrive to these conclusions in a way which is as objective as possible, which does not depend on our opinions, and also in a way which can be repeated later. And so doing this automatically, doing this with the statistical methods is the way to do that. So what I would like to do, and probably many of you are familiar with that, I would like to review essentially hypothesis testing with the t-test and analysis of variance. And probably many of you have seen this, but I think it's really important for us to look into this carefully so that we are all on the same page in terms of what is actually happening with hypothesis testing. And once I'm done telling you how great t-test and p-values are, then I will tell you how bad they are. Okay? So that's the plan. Okay, so just to remind you what we discussed yesterday, this is what happens in a statistician's mind and in my mind when we think about experiments, in particular in mass spectrometry, right? So we have two populations, and they have some constant protein abundances. So this is the mean of the abundance of the protein in a healthy population. This is the mean of the abundance in the disease. So we use the Greek letters to indicate that these are unknown. And then we include subjects into our study, and subjects are included randomly. There is a natural subject-to-subject biological variation. So we do not know exactly the abundance of the proteins in the subject, so we also denote their abundances as Greek letters. What we actually see is the intensities of peaks in mass spectrometry, which we observe, so this is why they are in Latin letters. And we observe them for each biological replicate and potentially even in multiple technical replicates, potentially even with multiple features such as peptides or peptide ions per protein. And then what we need to do is to aggregate this somehow and use this to make statements about the unknowns, right? About the difference between the means. And we need to watch out for the variance and for the inefficiency. So for today, I will assume that the protein is quantified with one peak on the spectrum in one run, to keep it simple. Next week, we'll talk about how to actually aggregate multiple peptide signals and so on for protein quantification. So for today, we just have one number per person, per protein. Okay? And we, in fact, will have one protein for most of the discussion, right? So that's what's going on.
Sorry?
Yes, please.
I'm not really sure for the spectra. I assume I is like in density, but what's L in the end for the index?
Yeah, so here it's really general. So we have, so the first, that's right. So we have 1 and 2, okay, here. 1 and 2 stands for the groups, right? So here K stands for the index, I for the subject, I stands for the protein, and L stands for the feature, potentially, right? But so what I'm doing today, so this is just for the in general, right? But what I will do now to make it much simpler than that, we have one number per subject.
So I and L equivalent. I and L equivalent to 1.
Exactly. And we just have one protein. Okay. So I already mentioned this yesterday. We will do everything on the log scale. So the very first thing that we do, as far as mass spectrometry experiments go, we will take peak intensity, we will take a log of them. And if we do that, then we're really interested in differences as opposed to ratios. And so we looked at pictures like that yesterday where we're interested in differences between the two groups on the log scale. And by the way, we will stay with the goal too, where we compare the averages of protein abundances between the groups. However, this is a question which is often asked, okay, but you know, in analytical chemistry, I'm always doing ratios, right? So what does it mean on the log scale, taking averages, comparing them, versus looking at the ratios? So I prepared this slide just to kind of put this in perspective. And really, we won't have too many formulas here. This is one of the, on the kind of more formula side. So if we want to compare two conditions, and we're interested in overall in group 1, is the protein abundance regulated compared to group 2 or not? So we need to aggregate somehow all the abundances of the protein in each group. So if we want to do it on the original scale.
Yeah, is there any difference between 2 log 10 conversion?
Not really.
No.
So the question was if it's what the base of the log 2 or log 10. The only kind of practical use of that is whatever you like to think, in which terms you like to think, right? And we use that. The more important thing for us is that we go from ratios to differences. And that's really the use of the log. And so when we are interested in a fold change, so we would be interested in a typical value in group 1, how it relates to typical value in group 2, right? So this would be the definition of a fold change in this context, right? If we compare the representative values, or right, the typical values between two groups. So if I take the log of the ratio is the difference between the logs. So this is the important one. So what I would like just to kind of, it's a side comment, but I think it's important for us. So what we will end up doing, we'll take the average of the log intensities in this group and compare to the average of the log intensity in this group. How does it relate to fold change? Well, we can actually write it out. So here I'm writing the average of all the intensities in group 1 minus the average of all the intensities in group 2 on the log scale. So now next line, I'm spelling it out. I replace y with the log of x. So x was on the original scale. So now it's the difference of the sums of the logs. Now logarithm has a property that sum of the log is the log of the product. So I can replace it with this expression here and this expression here. And now the difference of logs is the log of the ratio. If it's difficult, don't worry about that. The important thing is that now we can look at this expression and we can compare this to this expression here. So essentially what it means that our log fold change is the log of the fold change, where the fold change is looking at the geometric means of the intensities of peaks on the original scale. So everything I will talk about this hour is taking the log, taking the mean of the observations in each group on the log scale, and looking at the differences. And we will go over that. However, if you really like to think in terms of ratios, what it really means is the log of the ratio of the representative abundances in each group, where representative is defined as the geometric mean of different densities on ratio. So that's just to kind of put it in perspective.
It's probably a stupid question, but now each colored dot is one protein, right? Somehow.
1%.
So now we are comparing in this
no,
example proteome.
No. 1%. For the whole hour until almost the very end, I have only one protein, right? So here blue dots are people from the healthy group for that protein, right? So, and this is actually a really important comment. To compare protein, the abundance of protein 1 to the abundance of protein 2, we need to make sure that the peak intensities are comparable. And we of course know that they will have different amino acid sequence, different ionization, different interferences. It is a very different proposition to take the same peptide, which has the same chemical properties, and look at this across multiple subjects. So what I'm talking about here today is really looking at the same peptide or same set of features across multiple subjects. And some of them come from healthy, some of them come from disease. I want to know if the representative value on the happy or on the healthy is comparable with the representative value on the disease. So, okay, so we're not comparing proteins here. Okay, so now to do that, as we discussed last time, we need to essentially distinguish signals from noise, right? So we need to say, okay, what is the change between the groups, which is more systematic than what we would expect by random chance. So for that, we need to define the signal, right, the change between the groups, and we need to define the noise. So what is the random chance in this situation? So the signal here is, as we already described, so this is the difference between the means on the log scale And so the denominator here is our noise. So we are building the signal-to-noise ratio. And so we will be using the signal-to-noise ratio to essentially distinguish signal to noise, right? So now how do we do it? There are multiple formulas here, so let's kind of parse it a little bit. So first of all, this S1 squared is the variance of these blue points, right? So this is protein abundances across multiple subjects in the healthy group. S2 squared, calculated the same way, is the variance just from the data, right? Sample variance in the disease group. And so now we take it here and we divide this by the sample size in the healthy group, and we divide this by the sample size in the disease group. So this is known as the whole denominator, is the variation that we expect from this particular signal. So how does it work? So now let me take a little bit more kind of details, look into more details here. So if I look at the circle expression here, so this is the variance of the data divided by the sample size. So this particular term, this actually is describing how much variation we have in the mean of the group 1. So how confident we are in the mean of the group 1. So larger terms means that we are less confident, smaller value of this term means that we are more confident. So let me illustrate that. And so this is an example from this points of significance vignette, which I think is very, very useful. So this, let's look at this column here. So this is the abundances of one particular protein in one group, let's say in the healthy group. So what we're doing now, we'll take 3 subjects from this population and calculate the mean. Take 3 other subjects from this population, calculate the mean. Take 3 some other subjects from this population, calculate the mean. So the histogram here is the histogram of those means. If we keep collecting 3 subjects and calculating averages and plotting this histogram. Now here we do the same thing, but we take 5 subjects. So we take 5 subjects from this population, calculate the mean, 5 other subjects, calculate the mean, 5 other, calculate the mean, and then we draw a histogram of those 5 subjects. So this is what happens if we have 10, and this is what happens if we have 20. So what do we see? We see that if we have more subjects, so their histograms are much more narrow, meaning that their means are more similar to each other from one set of 20 subjects to the next set of 20 subjects. So the mean is more likely to be the same, right, or similar, right? So the mean is more likely to be reproducible. If we take only 3 subjects at a time, the means is more variable because it's based on less data. So what is also interesting is that these distributions, they're kind of bell-shaped. So we start with a normal distribution, but these histograms, they're also kind of distributed with the bell shape. Now what is even more interesting, that if we now start from something else, which is not at all normal, kind of asymmetric, we start with something really weird. We have this weird distribution. And we repeat the same exercise, take 3 data points, calculate the mean, 3 other data points, calculate the mean. We see that the histograms of the means, they become narrow and narrow, and they also become more and more bell-shaped. So this particular phenomenon is called a central limit theorem, which tells us that when we start from any distribution and we have larger and larger sample size, our histograms of the means will be centered around the population more and more, and they will be looking more and more like normal distributions. And the distributions here, all of them, they're called sampling distribution of the mean. So how much variation in the mean we'll have, we'll continue collecting the samples of the same size. So now if I go back to my previous slide, this expression S squared divided by n, this describes the variance of these distributions. So it tells us how much uncertainty we have in the means based on the sample size of n. And so it's very clear that n is the denominator. So the larger the n, the less variance you will have, right? And at the same time, the s is numerator. So the larger is the variance of the original population, the longer it will take for us to become
I have a question.
Yes.
How could be that in uniform distribution, the mean give a Gauss distribution?
Well, because the mean is based on multiple data. So if you have a uniform distribution, you will take something from the beginning, something from the end, you would average around the center, right? Next set of data points, you take one from somewhere in
It should
one
be
place.
always uniform distribution.
Not the mean. Because to have a mean in this range, let's say you have 20 data points. To have the mean of the 20 data points in this corner, you need to have all the 20 replicates in this corner, or the majority of them, right? Because it's uniform, if you have 20 replicates, you are less likely to have all the data coming from here. They will also come from other parts of this distribution. And so averaging them will be closer to the center. So it's very rare that you'll have 20 observations and they will all come from this part of the distribution. It can happen, but it won't happen systematically. Okay, so now this term tells us this is the variance of the sampling distribution of the mean. Now if we take the square root of this, this is the standard error. In other words, we know that variance is standard deviation of this distribution, right? So this is the original distribution in the population. The variance and the standard deviation of the sampling distribution of the mean, especially the standard deviation, this is called the standard error. So standard deviation tells us how much variation we have in the population in the first place. Standard error tells us how much uncertainty we have in the mean over that many replicates. And so now we do this for the mean of the first group, we do this for the mean of the second group, because we look at the differences, the uncertainty adds up, and then we take the square root to make it on the same scale of the original observations. So this becomes our signal, and this becomes the standard error of this comparison between the two means. So this is the signal, and this is the means. So this is how we build this, and it's very well justified that from this type of argument, that if we start from something really weird, our mean is still distributed around the true mean and approximately normal. Okay, so this essentially tells us, okay, this is how we build the signal-to-noise ratio. We still don't know how large the signal-to-noise ratio should be to actually claim the signal, right? And so this is the next step for us. So, as I said earlier, we would be interested in comparing the population means between the means of the two populations. So we want to know, our real question is whether mu1 is different from mu2. Or in other words, if mu1 minus mu2 is 0 or not. So this is our real question. We don't know what these values are. We'll never know. What we can do, however, we can make assumptions. So let us assume that in reality, there is no difference between the means of the two underlying populations. So this is what is called status quo, something we may not be interested in potentially, right? In statistical language, it's called the null hypothesis. So we hypothesize that in reality, there is no difference between the means in the large populations. And then the alternative hypothesis, in fact, is the opposite of that, right? So in fact, that there is the difference between these two means is not 0. So now, and this is really where things become interesting, if we build this signal-to-noise ratio, if we assume that there is no difference between the two means, we can use this type of argument either exactly or approximately to describe what would be the, what would be the plausible range of values that the signal-to-noise ratio could take if, in fact, there was no difference. Okay, let me repeat. So if we build the signal-to-noise ratio, if we assume that there is no difference between the two groups, if we also assume that each our subject in the study is independent, then we can describe the range of values of the signal-to-noise ratio, which we would see if, in fact, there was no difference between the groups. And we will do it mathematically, just from analytical derivations. We could show this format. Now, if our data have exactly normal distribution, so then the signal-to-noise ratio will also have a bell-shaped normal distribution. If our data are not normally, so if our data are not normally distributed, well, if it's normally distributed with unknown variance, it will be a distribution which is very similar to normal distribution, which is also bell-shaped, which is described as a student distribution. But if our data start with something weird, like we had here, then we can do central limit theorem that they say that the means are approximately normally distributed. And then we can say that this plausible range of values is approximately distributed as a normal distribution. as a bell shape. So this will be our reference. So now what we will need to do, we'll need to say, okay, but this requires us to assume that there is no difference between the two groups. So this requires us to assume that the null hypothesis is true. So what we'll do now, we'll actually calculate the signal-to-noise ratio from the data using the observation that we have, and we will overlay this on top of this graph. And we will compare this to where the graph, to where this is located on the graph. So for example, if I calculate the signal-to-noise and it falls right in the middle of this range, then we'll say, yeah, well, it's exactly in the center of the range that I expect, so there's no surprises. Therefore, everything I assumed is plausible, including the fact that I assumed that there is no difference between the groups. On the other hand, if I calculate the signal-to-noise ratio and it falls somewhere very close to the tail of this distribution, I will say, wait a minute, it's really far away from the bulk of this range of the distribution, so it's very unusual. So something is wrong. What is the first thing that can go wrong with my assumptions? Well, the first thing that is wrong is that I assume that there is no difference between the means and the population. So I'm saying that there's evidence against the null hypothesis. And so the last thing is, okay, so how do we decide how far is it from the bulk of the data versus how close it is to the center? So these probability distributions have a property that the area under the distribution corresponds to the probability of observing the data in this range. So for example, I can select this cutoff so that the probability to the left plus the probability to the right of this cutoff together in some pre-specified number, such as 5% or 1%. So this is our alpha, this is called type 1 error. And so these values, they are defined such that the probability to the left plus probability to the right is 5%, meaning we have 5% of chance to see values that extreme from this range without being wrong in our assumptions. And so now if we overlay the signal to noise on this distribution, we will say, okay, if it is inside this range of values, I will say there is no evidence against the null hypothesis. If it falls in outside, so in this red range, then I say it's too extreme, because we only have 5% of chance to observe something that is true. And so then we say that this is evidence against the null hypothesis, and we would say that we would reject the null hypothesis because our observed signal to noise is too extreme. So the very last thing which we can kind of describe here is the p-value. So how does p-value relate to that? Well, I can actually overlay the signal to noise here. And because it is symmetric and because we don't know in which direction the regulation will go up or down, we overlay this on both sides. And so now we can calculate the p-value as the area to the left of this curve, plus in this curve, plus the area to the right in this curve, as compared to our observed values. So the area to the left of the negative observed signal to noise, plus the area to the right of the positive value of signal to noise, is the p-value. And so we see already that if the p-value is less than alpha, it means that we are in the rejection region. And if the p-value is larger than alpha, it means that we're not in the rejection region. Question? Oh, I thought there was a question. Well, let's ask questions. Does it make sense? So let me now kind of rewind this a little bit and let's see once again, right? So what did we do? We made some assumptions. So the assumption is that there is no difference between the groups. We also made additional assumption that each data point is independent. And so now we will build the signal to noise ratio, which is motivated by this sampling distribution of the mean. And we will now consider how large the signal to noise is. And we will benchmark this against how large it should be using the theoretical argument which says that if there is no difference between the groups, we know exactly what is distribution. And if the data start from being normal, we can say exactly what the distribution is. If the data are starting from something that is not normal, we can say approximately what is distribution.
How to check if your data are normal if you have sometimes 3 or 4 points?
If we have 3 or 4 points, well, you know, if you don't have enough data, I say you don't have enough data, right? So if you don't have enough data,
it's typical for biology, if you need more biological indicator.
It is typical, it's not a good thing, right? But and the reason why it's not a good thing is because the only substitution to the data is the assumptions. So if you cannot see it from your data somehow or check it, then you have to assume it, right? And at some point, your conclusions are as good as your assumptions, right? And it's kind of difficult. So if you don't have enough data, another thing that happens is that if you start from something that is not normal, as I just said earlier, we can claim the central limit theorem, we will say that our signal to noise is approximately normal, but this only happens when your sample size is relatively large. So when you have 3, you see that this is not quite a bell-shaped distribution, right, if we start from that. So essentially, if you don't have enough data, first, you cannot even check if your assumptions are plausible, and second, if they're not plausible, essentially your conclusions will not be correct. What this really means is that when we make the decisions here, we are claiming that we have probability of 5% to reject the null hypothesis when in fact it is true. But in reality, because your data don't satisfy these assumptions, it can be a lot more. So in fact, you can have a lot more false positives than it looks. That's really the price.
How many data points you need to make a conclusion? What kind of data?
We'll talk about this tomorrow,
Okay.
and we will see. But usually, especially if it's real biological system, 3 or 4, it's little. Unless you are in a super controlled, model organism which has very little variation. But when we talk about humans, 3 or 4 is nowhere even close to it.
But if I were to counterbalance that, if I go like p-value from 0.05 to 0.001, this would help or not?
No.
So how then can I adjust my assumptions?
So, let's see. This is actually a really big philosophical question, right? So, what you should be doing is defining your analysis strategy before seeing the data. So if you say that you're going to use a t-test, right? So what does it mean? You say, okay, I either can demonstrate that my data are approximately normal, or I will have a large enough sample size to say that the mean is approximately bell-shaped, right? How do you know that? Well, you can know this from your pilot studies. You can know this from historical data, right? That this type of organisms, this type of stresses, this type of measurement system has this particular property, right? And then you do that, because the danger is, you start collecting the data and you set out saying, okay, I will use alpha equals 0.05, and then you'll say, oh, it doesn't look good. Let me use 0.01, or like 0.1 instead, right? And then still doesn't look good. Let me use 0.2, and you will kind of keep changing your, goalposts, until it tells you what you like. So this becomes very subjective and very specific to the person who looks at the data.
No, but if I were to go the other way around and make my p-value more
Even more
stringent,
conservative.
because I need to look at my data, otherwise I can never judge it.
Well, so you need to look at your data, but you also cannot make your decisions just based on what you see, right? Your analytical strategy has to be defined in advance. Now, it is true that by being more conservative, you are less likely to make false positives. But what can happen is that you also will not find any true positives, right? Because the easiest way to not make any false positive is to not find anything, right? And so this is not what we're looking for. And so so my point is that you will be using your data and your resources more efficiently if you check your assumptions in advance. You develop an SOP, and you will go into this experiment knowing that the assumptions will likely verify. And you will be using this SOP for the entire experiment. This is really the most efficient use of the resources. Now, otherwise, what you can do is, well, essentially you can do anything you want, right? So you can, you can pick your targets for follow-up in any way you want, right? But in the best case, you will just waste your resources, right? In the worst case, it can really lead to claims which will not be substantiated down the road. And the reason why I'm saying all of that, it's not because, statisticians like to do things a certain way, but it's really because that's what maximizes reproducibility. That's the real reason.
I was thinking, why not use a non-parametric test? Because
it's a very common question. So essentially, right. So the question is non-parametric tests. So can we have some other summaries which will make fewer assumptions, which will always which will lead to some other reference distributions like that, which don't require, for example, normality, right? So it is a very general case in statistics that the less you assume, the less sensitive you are.
Power will not be high.
And I would argue that if you assume less, and if you still want to be sensitive, it means that you need a much larger sample size. But if you have a larger sample size, then your central limit theorem kicks in. So in my personal practice, I never really see a need for non-parametric tests, because either your sample size is too small to do it, or you can rely on the central limit theorem.
So sample size being small and not normal data is not good for any test.
It is not good, yes. So there's always a price to pay. So if you assume less, it means that you need more data. That's really.
How does the is in proteomics?
Can you speak up?
Sorry, just because the technical limitations of it, you're biased towards more. You can be more abundant things. So it's like any proteomic data set is not normal.
So you're asking whether proteomic data are not normal? Well, okay. So let's see if I understand correctly. So first of all, this is why we take the log. This is another reason. Clearly, we have our distributions are very skewed. So on the log scale, things become more symmetric. So if we look at this picture again, so we see that if we start from something that looks more symmetric, it's much easier for our sample distribution of the mean to converge to the right value, right? If we start from something skewed, it takes kind of more replicates to get there, right? So the log scale helps us with the skewness, right? So that we can start from something which is already more symmetric. So now your second question is, well, some proteins are more abundant. So if we compare the abundant proteins between the rods, this is no problem. I think your question is more if you have one condition where it's low abundant and another condition is highly abundant, right? That's what you're asking?
I'm wondering whether there's any problem in using normal, the statistics that requires a normal distribution of data on proteomic data, which is usually not normal.
Well, again, so log scale makes it more symmetric. I'm not saying it corrects everything, right? But it makes it more symmetric, right? And once you start analyzing the data on the log scale, so if you have a large enough sample size, it doesn't matter for this reason, because you are not comparing the individual data at this point, you're comparing the means. And the means are normally distributed, right, because of the central limit theorem. But if you have a small sample size, then your means have this kind of weird distributions. So what does it mean? It means that your alpha is not as you think it is, right, because your reference distribution is different. Or you use some other methods which don't require these assumptions, but these methods, they are less sensitive themselves. So in other words, no matter what, you're doing less well, right? So my solution for that is to collect enough data so that one, you can check your assumptions, two, you can more or less claim the central limit theorem, right? And the third thing is, especially when we start working with more proteins, so what you really care about is to rank your proteins in the right order. So even if your p-values are not quite right, so as long as you have the ranking in the right order, that's usually the very important first step. So long story short, in my personal experience, we never saw the need for doing things that do not assume normal distribution for these reasons. And I find that it's more complicated. So another reason why it's more difficult is because it's more difficult to generalize this to complex designs, to many proteins, and so on. So there are so many other things which contribute to this data, which can, affect our decisions. That I find that adding this extra kind of non-parametric assumption, I just don't find that it gives us enough benefits for that. That has been our experience, and it has been with quite a few data sets so far. But we'll talk about this next week, hopefully, if you stay, because for today I'm actually talking only about classical statistics, which does not even have any proteomics in it at all, or minimal, right? But starting Monday, we'll talk about, okay, how do we deal with missing values, covariates, multiple features which disagree and all of that. So that will be kind of more specific to mass spectrometry.
about mean distribution, we're talking about that per protein, right?
We're talking about one protein. So for my whole discussion right now, I only have one protein. I have multiple replicates,
Yes.
right? But I only have one.
But let's say in a shotgun proteomics where you talk about equal to make a normal distribution for every protein
That's right.
across your
And
sample.
each protein has its own variance, right, and so on. And it can have its own missing value, so it will change the sample size, right?
I mean, you also see that usually there's a normal distribution per patient, let's say.
This is less of interest to us, right?
Yes.
And the reason is because comparing protein 1 to protein 2 for the same patient, well, there are too many differences, right? Including ionization efficiency, including the digestion and all of that. So if you really want to compare abundances of proteins within the same patient, well, either you do absolute quantification, right, so that it really relates to the true values, or you have to do other things to make things comparable. So for the moment, I'm really talking about relative quantification for the same protein across multiple replicates.
For this figure, like if we take the very, very normal situation and I have 3 biological replicates of one particular group, then I wouldn't even have those distributions because these are like sample of several means and I would have only one mean across my 3 biological samples, right?
What do you mean? So we're talking about the mean of 3 biological replicates. So you
Yeah.
have one mean in the group.
One mean in a group, yeah.
That's right.
Okay. And then across several groups I would generate.
If you have 5 groups, you'll have 5 means. Exactly. So that's exactly what we do, right? And so this will compare group 1 to the mean of group 2. Exactly. And so let's kind of keep talking about the sample size. Another reason why sample size is important, right? So what I didn't quite emphasize yet that we don't know this variance, right? We also need to estimate this variance from the data. And if you have a very small sample size, so even your components of the signal to noise are unstable. So the means are unstable as we just looked at this, right? But then the estimates of variation can also be unstable. So this also comes from this vignette in points of significance. So what they do here, they take this weird distribution as before, and they collect data of sample size which increases up to 100. And so they repeat this simulation 3 times. So for each sample size, they look at the means and they show how the means fluctuate, right? And so you see that for the small sample size, the means are more variable. As the sample size increases, the means kind of converge to the true mean of this distribution. So far, so good. But they now do the same thing from standard deviation, right? So standard deviation is the square root of that, right? So how much variation we have. And so take a look at what happens, right? So they repeat it 3 times, and they collect the data of the sample size and until the sample size increases. For the mean, it fluctuates kind of up and down, above and below this horizontal line. For the estimate of variation, it tends to be below. What does it mean? It means that our estimate of variation tends to underestimate the actual variation in the population. And the reason is this: if we only have 3 replicates, it's possible that we have 3 replicates from this part of the distribution just by random checks. So when you calculate standard deviation, it only reflects this variation. The data don't really indicate that you have this possibility in this range as well. So if you have more and more data, then it will start covering the entire range. You have more and more variability. But if you have 2 or 3 points, it's very easy to make it seem that you actually have very little variation when in fact you just didn't have a chance to sample the full spread of possibilities. And so for small sample size, it means that essentially you underestimate the noise that you have, and it looks like your signal is very important. But in fact, this was because we underestimated the extent of variation. So this is how it can also lead to false positives. Okay, so I will skip this in the interest of time. So we talked about the signal noise, we talked about the type 1 error, and we talked about the p-value, right? So hopefully we're on the same page now. So another way to report the results is in terms of intervals. So the problem with p-values is that, well, the good thing about p-value is if you have a list of many proteins, you can just kind of compare the p-value less than 0.05 or not, and then you make your decision. But then you kind of lose the information about was it upregulated, downregulated, by how much, right? So you lose all of that. So using intervals would be another way to keep this information, but also provide a sense of how much uncertainty we had in these log fold changes. So we already talked about, and so usually in reports, when we report our results, we report this in terms of error bars, right? And so error bars reflect how much change we have, but they also reflect how much uncertainty we have. So what can be in the error bars? So we can have actually at least 3 types of error bars. So the first one can plot plus minus standard deviation in the population, which it will tell us, okay, this is how much variation we have in the actual data. We can also plot plus minus standard error of the mean to tell us how confident we are in the mean of the data. So these 2 things will be very different error bars. And the third interval, which we can also use, is the confidence interval. So for example, here the confidence interval will take our signal. It will take our noise, exactly what we had on the previous slide. And so now we will just have this multiplier, which is actually this cut of the red line on the left and on the right side. So the confidence interval is built exactly from the same argument, where we know what is the expected range of the signal-to-noise value if we didn't have a difference between the 2 groups. But now we flip it, right? We keep this on the right, we take this and we multiply it by this cutoff that we have here. And it gives us a confidence interval. So this is our signal plus minus our noise multiplied by this cutoff. So again, this T alpha divided by 2 is this cutoff, such that we have the area to the left plus the area to the right equals to alpha. So having a error bar plus minus standard deviation or plus minus standard error doesn't really have a probabilistic interpretation. It just says, okay, this is how much variation I have in the population or in the mean. But here now, the definition of the confidence interval, it's a procedure which builds the lower and upper limit like that. And confidence interval, it's actually not an interval, it's a procedure, it's an algorithm. And the definition is like this. So if I want to have, for example, a confidence interval for one mean, I have a procedure which gives me the lower and the upper limit. And I collect the data 100 times. And I use this procedure to draw 100 of those intervals. And 95% confidence interval is the procedure such that 95 of these 100 intervals will contain the true value. Okay. So confidence interval is a procedure where you collect the data 100 times. You use this procedure on your data set 100 times. You get 100 intervals. 95 of those will cover the true value, and 5 will be outside. So why 95 and why 5? Because these are the cutoffs which were used from our reference distribution, such as the area to the right and the area to the left combined to 5%. And so the value of the confidence interval is to say, okay, how likely are we to actually contain the true value? And again, if we make this assumption that our data are independent and our means are exactly normal or approximately normal, we can derive these procedures which will contain the true value exactly or approximately. And so now, what does it mean? It means that we have at least 3 types of error bars. So if somebody makes a plot and says, here's the plot and here's an error bar, don't believe them. Because they need to say what kind of error bar it is. Right? And because the error bars have to look very differently depending on what actually is the intention behind the error bars. And so let's take a look at that. So this is again from the points of significance vignette. So here they looked at 2 populations and they just said, okay, the difference between the groups is 1. And they provided these 3 types of error bars which look identical, right? So this edges touch, right? So this is standard deviation, this is standard error of the mean, and this is confidence interval. These exactly identically looking intervals correspond to very different p-values depending on what they represent. So in this particular case, if it's a standard deviation and it's always for n equals 10, it's actually a statistically significant difference between the means. But if it's a standard error of the mean, it corresponds to a p-value which would not pass the significance. And so here they do the opposite. They fix the p-value, n equals 10, and they show what the standard deviation, standard error, and confidence interval will look like to give us the same p-value. And you see that it looks super dramatically different. So in fact, for standard deviations, we can tolerate quite a bit of overlap between the populations because we're not comparing the variation in the population, we're comparing the variation in the mean. And if we have a large enough sample size, we can be quite confident in the mean, even if we have large underlying variation in the populations. But if we're talking about the variation in the mean, so standard errors, then we'd better be different quite a bit, right, to have the same same p-values. And the confidence interval can tolerate some of the overlap, but not that much. And so now they also show how this, so this is for standard error of the mean, and this is for confidence interval, how it relates to the p-value. And you see again that the standard error of the mean has to be super different, and confidence interval can tolerate some overlap.
So if 95% confidence intervals overlap, I can still be 0.05 p-value?
Exactly. Exactly. So you can see here, this is 0.05, and this is 2 confidence intervals. Exactly. But then for the standard error, you would expect a really big difference between these two periods. So now, which one to use? It really depends on what message you want to convey to your audience, right? So if you want to talk about how likely you are to contain the true value versus how much confidence you had in the mean versus how much variation you had in the underlying population. So these are very different summaries. And all of them, you know, have a value, right? But you just need to choose what is the point you are trying to make when you present that.
For that reason, does it the view to use more than one describer?
Oh, you can use anything you want to describe. You can have all of them, of course. And so that's not the problem. The problem is that sometimes people just say error bar, and they don't say what kind of error bar, and then you don't know what to make of it. You know, you can use all three. You can use 2 of the 3. You know, whatever you want, right? Just explain what they are.
But if the standard error of the mean does not overlap, it still doesn't have to be significant.
Exactly. Exactly.
So from the error bars alone, there is no way to deduce significance whatsoever.
Exactly, and that's my point. So it is useful, right? So this is different type of information, right? And so this is why we do all of that, right? Because all of these things, they reflect different information, right? But clearly, if it's very, very far away, right, it will be significant. If it's close, it depends, right? So these are different ways to look at the data. More questions, please.
So, so all this, when you have systematic error in your experiment, but like constantly read 10% over or under, all this becomes irrelevant, right?
So you will have a bias, and your t-test will not know about that. So that's exactly what we discussed yesterday, right? So let's say we had 2 populations, and you have healthy, they're all male, and disease, they're all female. You will find differences all right, and you will have variation, and you will have small p-value. But your method will not be able to tell you that this difference is there for the wrong reason. So this is a flaw of the experimental design. And this is exactly what I was saying yesterday, that this type of statistical methods, they cannot, compensate for the flaw of the experimental design. They assume that your replicates in each population are representative of the population. And if you have healthy are all male and disease are all female, they're not representing the populations appropriately, right? Because they sample with it biased in a biased way. And that's what happens, right? So this is the assumption of being representative of the population is very important. And this is not, well, I guess if you have some labels of the samples, you can kind of figure it out, but this really is something that you build as part of your experiment.
Is the calculation that you do to determine how many replicants you need to do?
We will exactly use this calculation. So for
Is that
example,
how many ends you need to go? What's this?
I can't quite hear you.
Is that like, is the result of that calculation when you go to your slide when you have the different distributions? Is that like,
This is exactly how we do experimental design. That's exactly what is happening. And we'll talk about this tomorrow. So what essentially we'll need to say, for example, one way to do this is to say, I want to design an experiment where confidence intervals do not overlap, right? Or maybe I want to have confidence intervals like touching like that, right? So what does it mean? Well, this is my formula for confidence interval, right? So what affects the width of the confidence interval? 2 things, right? So it's either the value of alpha, right? So if you want to have smaller alpha, you will have wider intervals, right? Because smaller alpha means that your cutoffs are large in absolute value, right? So it will affect your multipliers here. Or the sample size, because larger sample size will reduce our noise, right? So it will reduce the width of the confidence interval. This is exactly how we do sample size. you can actually, but what you would need to know for that is what is the value of the variances in the populations. So you would need to know, okay, how much variation I can expect from my new study, right? And then you say, and you can do it, for example, from pilot experiments, from historical data, and then you say, well, what would be the difference between the groups I'm interested in? And then it will essentially tell you what is the minimal sample size which will allow you to actually distinguish the confidence intervals. That's exactly how we do it. And so that's also to answering your question in part, right? So this is how we will see how likely we are to actually distinguish the signal from the noise. Okay, so this is for that. So now let's talk about statistical power. Statistical power is also a probability, and it's a probability of detecting what we want to see. So it's the probability of finding evidence against the null hypothesis when, in fact, there is a difference between the groups. So how likely we are to reject the null hypothesis when we have this difference. So this is, again, from the same points of significance collection. So this is our reference distribution. Let's just say by looking at one tail, just to make it simple, we'll put all alpha at one tail, right? So this is our signal to noise which we calculate. And we just said that if there is no difference between the groups, we can mathematically derive the range of values which we expect here, right? But now let's say there is a difference between the groups. Let's say group 1 has a larger protein abundance than group 2. So then the signal to noise, it will not fluctuate around 0. It will fluctuate around some positive value, right? Because there is really a difference between the two groups. So then the actual distribution of this, right? If we kept collecting the data and calculating signal to noise, it would look like that. So it will be shifted to the right. It will be fluctuating around something which is to the right of 0. And so if we're now using this cutoff, and we're looking in the rejection region at the area to the right of this cutoff, this is the probability of rejecting the null hypothesis when, in fact, we have a difference between the groups. So this probability is the statistical power. And so what we want to do, kind of going back to your question, how do we design the experiments? Another way to do it is to look at the statistical power. So how can we maximize our probability of finding the difference when, in fact, the difference exists? And so we can do it in multiple ways. This is a bad way. This is kind of, well, not quite what you suggested. It's the opposite of what you suggested. Let's increase type 1 error. Instead of having 0.05, let's have 0.12. Yeah, well, if we allow us more false positives, yeah, we will detect more changes, right? The price for this is more false positives. So this is not very good. A better way is to increase the sample size, right? So we just said that if this is what happens when there is no difference between the groups. If the first group is larger, so this will shift to the right, how can we make this histogram of signal to noise shift to the right more? Well, if in reality there is a bigger difference between the groups, it will shift to the right. But at the same time, if we have a larger sample size, see that sample size in the denominator of the numerator. So increasing sample size will shift this distribution to the right. And so it will increase our power, so the probability of detecting changes. So this is a better way of doing, keeping the type 1 error, so the probability of false positives as fixed. Okay, and so another way to do this is to have more complex designs, so I will have to skip it as well in the interest of time. So now going back to the sample size, so this is as a preview, this is exactly how we will do it. So we will need to know what? So now we know how to analyze the data, right? So we know what will be our procedure to detect differential abundant properties. So when we plan the next experiment, we can actually play out different scenarios. So we fix probability of type 1 error. So this is usually very kind of, standard. It's 5%, 1%, or 10%, right? So not much more. So now we want to know what will be a probability of false negative. So it is this, right? What is the probability of not rejecting the null hypothesis when, in fact, there is a difference between two groups? And this is something we can also set in advance. For example, let's say 0.2, right? So we want to have 80% chance to detect true change. what would be the minimum log flow change we're interested in? This is something also we can come up with. So what is difficult is to know how much biological and technical variation we have in our measurement system. So this is what we will need to learn from historical data. And so now what we will do, we'll calculate this noise term, right, which is this. And we want to bound this by an expression which involves all of these things. And we can draw a sample size curve where this will be our fold change, and this will be the number of subjects per group, where we solve for the number of subjects from here. So this comes also from a kind of theoretical calculation, but essentially if we can specify all of these terms, if we know how much variation we have in our population, we can solve for the sample size. And some things are very easy, right? You can see that if you want to have a smaller fold change, you will need to have a larger sample size to protect that, right? Or if you have more variance in your biological system or in your technological system, you will need to have more evidence for that as well. And so usually, and in fact, next week we'll talk about MS Stats. This is a tool from our group. So the way we deal with that is that every time we analyze a data set, we immediately think of this as a pilot study for something else. So we'll get this variance components, and we will draw power curves based on the variance components in this data set so that you can plan the next experiment. Okay, so let's take a little pause here and see if we can clarify some other things in terms of hypothesis testing, p-values, sample size calculation. I'm most happy to repeat again or say it differently.
So if you keep increasing the biological replicas, then as we were speaking yesterday, you're gonna see more of the difference, right?
Of course. So I think the easiest is to see it in terms of the confidence intervals, right? So if the sample size increases, your confidence interval will be as narrow as you want. So there's definitely a way to show anything as being significant with enough sample size. And the same thing with the statistical power, right? So because this is, if I increase this, my signal noise will be fluctuating kind of more to the right, and I will also increase my statistical power. So at some point, it becomes not really about statistical significance, but about practical significance, right? So even things that are statistically significant doesn't mean they're practically important. But usually, as we just heard, right, we rarely have resources to get to that stage, right? And so the question is, how can we conduct a minimum experiment with the minimum number of replicas to be able to distinguish some changes which can be of practical importance for us, right, and distinguish them from the noise? That's what we're talking about. Okay, so now let me talk about, we have half an hour, so this is good. So we can talk about the issues with p-values and how bad they actually are. So the fact is that even though there's a lot of good things about p-values, people tend to put too much faith in them. In particular, sometimes the studies are optimized for a particular p-value. And so we just need to make sure that my p-value is less than 0.05 and then I can publish. Things like that. And I would like to argue that this does not lead to reproducible research. So a p-value is essentially a score which allows us to kind of see, if there is a reasonable way of moving forward or not. But this is not the end goal, right? And this is not a confirmation that we actually see the true change. It is just another derivative from the data, another summary from the data that we're taking. And so let me illustrate that. So, but before I do that, I wanted to tell you about the statement of the American Statistical Association. So it issued a statement 3 years ago on the appropriate use of p-values. And let me tell you something. American Statistical Association doesn't make any statements on anything. So this was really very in a special case because there was enough confusion in terms of how we use p-values and what they mean. Do they actually validate our experiment? Do they validate our design, or something like that? So they're not doing anything of that. And so there was a group of statisticians who essentially wanted to express the intention behind p-values and how they should not be used. So p-values can indicate how incompatible the data are with a specified statistical model. right? So our model said there is no difference between the two groups, right? So p-value says, okay, it's not compatible because our signal to noise is too extreme for what we would expect to see. So it's not compatible with that. P-values are not a probability that the null hypothesis is true. It is also not a probability that the data are produced by random chance. So it's really a measure of how extreme our data are with respect to what we expect to see. But it's not a probability that the null hypothesis is true. Scientific conclusions and business policy decisions should not be based only on whether a p-value passes a specific threshold. So this is kind of to what you were saying, right? So if p-value is significant, it doesn't necessarily mean that we should invest money in that, right? We have to kind of think more about what it means. Proper inference requires full reporting and transparency. We should document exactly how we set our thresholds, and this really means setting up SOPs. And p-value or statistical significance does not measure the size of an effect or an importance of the result. So it doesn't tell you how big the fold change is, right? And it doesn't tell us how practically important this fold change is. And also a p-value doesn't provide a good measure of evidence regarding a model or a hypothesis. In other words, if my p-value is small, it doesn't mean that my data are normal, right? Or things like that. So we shouldn't really interpret the p-value as a proof of everything that we did was correct or anything like that. So now, let me kind of show you why exactly the p-value is actually very limited in terms of how we can use them. And this is one of my favorite papers, also from Nature Methods, which illustrates that. So these are two populations, A and B, and have a relatively small difference between the two groups, given the variation in them. And so what the researchers did, they took 10 observations, I believe, from each group, and they plotted them. And so you see that these are the means of these two observations. The difference is 1.46. The p-value is quite small. So you can kind of argue that they detected the difference in the means between the two groups. But then they did the same thing again, right? So they took 10 data points from each group, analyzed, and now they go back and they take 10 more data points and analyze them again. They compare the differences between the two groups, and now the difference is in the opposite direction, and the p-value is 0.8. Why? Well, because we had a lot of variation in the data, relatively small difference given the variation. So depending on how those 10 data points come about, they can be really different between the groups, but they may not be different between the groups. And so the estimate of the log fold changes in the opposite direction, and the p-value is very large. Now, do it again. So now the difference is 0.08, much less than this, and the p-value is also large, meaning we do not reject the null hypothesis. Do it again, it varies again. So in other words, p-value is a summary of the data. Because the data are random, p-value is a random variable. So if your p-value is less than 0.05, it doesn't mean that it will be less than 0.05 tomorrow, right? For another replicate of the data. So it is really not a validation of what we did this, right? So now they keep going. So instead of doing this 4 times, they did it 1,000 times. And now they plot the histograms of the p-value. So they took the log scale just because we're interested in small values, and so the log scale amplifies the small values. So here, they do this for the sample size of 10 data points. And you see that out of thousands of these p-values, only a small fraction here in gray is actually below the significance cutoff. Here we have all of these instances of simulations where we do not find differential anomalies. They increase the sample size. Okay, so now we have more. We have 469 observations in this part and quite a few here, right? Sample size 64, okay, more. So it took a sample size of 100 to consistently have p-values below the value of 0.05. So the p-value is a random variable, and even if you see it once as significant, it doesn't mean that you will see it significant again, and it is clearly a function of sample size. So you have small p-value just by increasing the sample size. And again, kind of going back to your point, you can argue, is 0.5 here a practically significant difference or not? Well, it depends on what you kind of want to do about that, right? So maybe it is really important, in which case you really need to have sample size 100 to see it, or maybe you shouldn't. And this is how the sample size calculation. And so they do another thing, which I also think is very insightful. So they repeat the same thing. So here they have for different sample size, they have this figure where they plot the p-value on the log scale on the x-axis, and you see that the p-value, well, they have, it's exactly the same thing as before, right? So they tend to be large for small sample size, and they shift towards smaller values for the larger sample size. But what they also do now, here on the y-axis, they have the estimated differences between the groups, right? The log-fold changes. But what they also do here, they plot histograms of the reported differences between the groups, but only in the subset of the simulations where we reject the null hypothesis. So only the simulation has p-value below 0.05, this simulation will report the difference between the groups in this histogram, otherwise they will skip it. And so take a look at what happens. So this is the y-axis is the reported difference between the groups. 0.5 is the true value here. You see that if we only have 10 replicates, not only the majority of the things are not significant, but if we report something as significant, we dramatically overestimate the difference between the groups. So all the reported differences are above the true difference. Now, if we have more replicates, so now suddenly they kind of start moving on the other side of 0.5, 64, a little bit more, and it's only 100 replicates. Now our reported estimate of difference between the groups fluctuates around the true value. So small sample size means what? We underestimate the true extent of variation. We may, so first of all, we may not find the difference, right, because we don't have enough sample size. We underestimate the extent of variation, and we overestimate the extent of regulation. So this is a recipe for many false positives, right there, that will not be verified later on.
How theoretical power is calculated?
How the theoretical power is calculated? Well, exactly like this. This is exactly the expression. So what I said here, I fix alpha and I fix beta, and I solve for the sample size. But really, it's an equation that links all of these terms. So what you can do instead, you say, I have a sample size, I want to know what beta is, or 1 minus beta, and you solve for 1 minus beta. So essentially, you fix everything except one thing, and you solve for the last thing. And in fact, it reminds me that oftentimes, well, we just have as many replicates as we have, right? We know we cannot have more. So what you can do then is to essentially say, okay, for this fold change, what's my expectation, right? So what is the probability of actually finding this fold change, given that I only have 4 replicates? That will give you a value that may be fairly small, right? And then you decide if you want to proceed with that.
What about multiple experiments? Let's say you have 4 biological replica and 4 times repeated experiment. Basically, you are 4 times selecting.
But these are the same replicates, you just repeat it several times.
Yeah, but
So
it's
you don't
different
have
day,
much of it.
different, sorry, it's...
It's the same. As
So-
I was saying yesterday, you have 1 person and you quantify it 15 times, it's still 1 person.
No,
So
no,
yes-
let's say it's... because...
Oh, if you have new subjects every
yeah,
time?
exactly.
Well, so yeah, so that's much more meaningful, right? So then you would be able to combine this data, but you will have to be very careful, right? Because now you have, remembered batch effect yesterday, or the day effect? So if you do it on different days, so you will have a day-to-day variation, which is part of that. So if you have the 2 groups in each day, you have to do this blocking technique, right? Where you look at the differences within each group, right? And then you combine the differences.
Okay.
Right? So that's possible.
Will we talk about how to analyze this paired data later on in the course?
To some extent. Well,
Because it's not so straightforward anymore than if you block.
that's right. Let me see. We'll try. It is that, so the point you're making is exactly right, that when you start having blocking effects, and especially if you don't have an equal number of replicates in each block, it is non-trivial. And I'm not sure, well, we'll see. We'll do our best. Okay? So, let's see. Questions on this side, I kind of keep moving. Questions on this side. On both sides. Okay, so this is what happens with the p-values, just in terms of their variability, right, and their dependence on the sample size. Oh, and here they also do the same thing for confidence intervals, right? So when you have only a small number of replicates, your confidence intervals also fluctuate, but when you have more replicates, they become more narrow and they're more stable as well. Okay, so this is for confidence intervals. So now, we talk about another problem with p-values, which is the fact that it's not designed for experiments which are very typical in mass spectrometry, where we have more than one protein. Because what we started with is to say, okay, what is our alpha, right? It's the probability of making a false positive discovery, right? And then we use this to make a decision, right? And so on. But what happens when we start doing this over and over and over for each protein? So, for example, for us, when we implement this in MS stats, we pretty much write a loop, right? We say looping over proteins, do the same thing over and over for each protein. So what does it mean? Okay, so, well, if we keep doing this, right, so there's some probability of false positives, let's say it's 5%. But if we do it for many proteins, let's say if we have 100 proteins, it means that we have 5 out of 100 will be false positives, right? If we have 1,000, we have 50 false positives. If we have 1,000, we have 500 false positives, right? So this is not really good. And this is an example. I have several examples from Jeff Lick, who is a biostatistician at Johns Hopkins. So he brought up this poster where scientists did a functional MRI of the brain of dead fish. So the fish is dead, right? And they're measuring brain activity of the fish. And the way fMRI works, there are many different regions where they essentially test for activity, using methods very similar to what we discussed here. And if you have enough regions, and if you test enough, you will always find something. If you look hard enough, you usually find things, right? And so they found many active brain regions there. And so these active brain regions, they're just false positives. And if we have even a small probability of finding false positives, if we have many regions, we will do that. So this is very much the problem in proteomics, especially when we are going for bigger protein lists, when we're trying to, have bigger coverage, more fractionation, or whatnot. So this problem becomes really exacerbated. Oh, so this is another one. This is where you can also look for another app where you can do the hacking of p-values like that. So let's take a look at what happens if we have two proteins. This will be kind of a simpler case. So remember, we build our signal to noise, right? And we compare this with our reference distribution, which we expect to see if there is no difference between the groups. So this is what happens for protein 1. I just flipped it here, kind of upside down. And so now this is alpha over 2 and alpha over 2. These are probabilities of false positives, right? So what if we reject the null hypothesis when in fact there is no difference between the two groups? And we do it regardless of what happens for protein 2. So this kind of, for any value of protein 2, protein 1 have this probability of rejection. Now, for protein 2, it's the same thing. So if we have this distribution, so the area in the tail is our rejection region, we reject the null hypothesis, and we do it regardless of what happens for protein 1. So now this area is the probability of a false positive for protein 2. But our experiment has both proteins. So the probability of having at least one false positive is actually both of these areas combined, which is, of course, more than 0.05. And this is just for two proteins, and if we have 10,000 proteins, the probability of at least one false positive is 1. So we're guaranteed to have at least one false positive in these cases. So how can we deal with that? Well, clearly what we need to do is to be more conservative. So we want to control the overall area, so what we can do is to push our decision boundaries back towards more extreme values, such that the area outside of this dashed line becomes what we want, let's say 0.05. But what this means is that if we are more conservative, it means that it becomes more difficult to reject the null hypothesis for each individual protein. And so a lot of work is going into how do we push these boundaries back enough to control the area outside of it without being completely conservative, so that we require some extreme signal to noise values. And so many of you probably have heard about Pvalue approach, where we take alpha and we divide this by the number of proteins. Well, that's exactly what it will do, right? It will take our alpha and now divide it by something. So our decision boundary will be much more conservative. And it works, except that if we have alpha 0.05 and we divide it by 10,000 proteins, we are really requiring extreme evidence for that, right? So we're looking for other ways which would be less extreme, but would still allow us to control some kind of overall rate, error rate, which would have understand how many false positives we can have and how often. And so this has been especially when gene expression microarrays appeared, there was a lot of very active statistical research in this area. How do we determine these boundaries? And there's quite a few methods which are doing that. And I will just talk about one which, in our experience, is the easiest to use, the most robust to both assumptions and also just numerically the most robust. So in 1995, I think, so Benjamin and Holmberg, these are two scientists who essentially said, you know what, maybe the problem is here not only necessarily in the decision boundary, but it's in the problem is in how we define the error rate in these experiments in the first place. So here, this area indicates the probability of at least one false positive in at least one protein. And maybe this is too much to ask in experiments which quantify too many proteins. In fact, if we quantify 10,000 proteins, maybe we're okay having at least some false positives, as long as we can control what is the proportion of false positives in the overall list of differentially abundant proteins. And so now, instead of controlling the probability of having at least one incorrect decision, so this was our alpha before, we define a multivariate error rate, which is the proportion of false positives in the list of the proteins which we claim as differentially abundant. And this is false discovery rate. If you were here in the beginning of the week, you certainly heard about false discovery rate for identification of an SMS spectra. It is the same concept, but now it is applied here for quantification. So if you are doing DDA, for example, and you do database search, you have one F0 there, and now we have a second F0 here specifically for quantification. Okay, so so there are many methodological considerations here. So how do we define these error rates and so on? So this is how this original paper represented that, and this table is still very widely used to the date when we talk about multiple testing problems. So this is the truth. This is how many proteins are truly non-changing, not differentially abundant, and this is how many proteins in our experiment are truly changing. We have M proteins total, M0 are not changing, the remainder are differentially abundant proteins. So now the columns are our decision. So this is how many proteins we claim as not differentially abundant, and this is how many we claim as differentially abundant. So let's say we claim R as differentially abundant, so the remainder are not differentially abundant. And each combination here are these numbers in the table. So the problem is that the only thing that we really observe is R, right, and M minus R. So these numbers in the table, they're actually not observable. We don't know what they are. The only thing we know is this number. And so a lot of statistical methodology essentially tries to understand what would be the plausible values for these counts in the table. So type 1 error rate, which we just discussed earlier, this is in the very beginning. This is the probability of making a false positive decision. So this is the probability that we are here, right? So it's truly not changing, but we claim it's as changing. And it's the average V divided by M0. So this is if we have one protein. So on average, is characterized the error rate for one protein alone. Bonferroni controls family-wise error rate. It is the probability of at least one error. So it would control the probability that V is anything but 0. So if we divide alpha by the number of proteins, we will say that then our procedure will have the probability of alpha that we have at least we have no false positive, non-positive results. So this is very conservative. And so false discovery rate will say, okay, we can have some false positives, so I want to control the average ratio of V divided by R. So technically there's some technicality here. We don't want to divide by 0, so we'll look at the maximum between R and 1. In our experiments, we always find something, so it doesn't really matter. So we want to control the ratio of V divided by R. And here we have the expected value. It is what means that what happens if we keep collecting data and applying this procedure on average, we want to have this V over R ratio equals 5%, 10%, whatever you want. And so there was a lot of kind of methodological work, analytical work, which will tell us what are the procedures which guarantee that our decision gives us, on average, this proportion of false positives. And so, in terms of Pvalue, which controls family-wise error rate, so the procedure will be calculate p-values, then reject the null hypothesis. Is the p-value less than our alpha for the entire experiment divided by the number of proteins? And now we can also restate this in an equivalent procedure using adjusted p-value. So if the p-value is less than alpha divided by m, it's the same as multiplying p-value by m and compare it to alpha. And so the adjusted p-value will be p divided by m. And then we kind of bound it to 1 just so that the p-value, adjusted p-value stays between 0 and 1. And we compare the adjusted p-value to 1. And now for discovery rate, controlled by Benjamin Hoberg, and this is what is implemented in MStats as well, has this approach. So we order the p-values from the least significant, so the largest value, to the most significant, to the smallest value. For the smallest p-value, we do exactly the same thing as Pvalue. We take the p-value and compare this to 1 divided by m. But for the least significant, we don't adjust this at all. And so everybody in the middle has this kind of adaptive procedure like this. And we will compare this, from this order to here, and the first time we have a significant protein, we keep everything as significant. And we can also have an adjusted p-value where now we multiply the p-value by m divided by k. I realize I'm going a little bit fast, I just want to stay on time. However, we will have a chance to practice this, especially those of you who stay next week. We will look into this a little bit more. So, in other words, there are ways to control the error rate when we have many proteins in our experiment. But of course, the price for this is that we are more conservative, because now we don't compare this with 0.05, but we compare this with some small value. Okay, and the very last point I really want to make in the last 5 minutes is that everything that we discussed so far really doesn't address all the pitfalls that we can have in the analysis of the data that we generate in mass spectrometry experiments or in any other experiment. So I had a colleague once who told me, well, you know, this adjustment for multiple testing, adjusting p-values for multiplicity doesn't really work for me very well, because I had small p-values and I was very happy, and then I had to adjust for multiplicity, and then suddenly all my p-values became very large, so they're not significant anymore. So something is really wrong with this p-value adjustment. Can we not have it? And so it was interesting to see that everything kind of was was stuck on this adjusted p-values. Because if we think about what's going on, right? So what did we actually do, right? We designed the experiment, we collected the data. Let's say it's DDA experiments. We did a database search. We did peak detection, quantification, so on, right? We created a report, which we could read, for example, into R. We specified some modeling assumptions. And then we did some analysis, right, to get the p-values, and then we adjusted the p-values for multiple testing. And we get the result we don't like. So is it the fault of the p-values, or is it the fault of the entire procedure? So it's really the entire procedure which may have led to the results which you didn't expect to see from this particular experiment. So it is really every single step along the way could lead to something going wrong, including things such as wrong assumptions, including things such as insufficient sample size, some mistakes in data processing, some mistakes in like how we do things, right? And so this is actually Jeff Leake, the same statistician, and his colleague, who essentially say, yeah, well, you know, when we have these large experiments which have many mistakes, we should not be blaming p-values when things go wrong. We should really think about what happens along the whole, you know, chain of steps that we need to do to actually arrive to the conclusion. And statistical considerations, they're really everywhere, right? And they're really part of reproducibility. And there are some famous examples which show how different decisions which are made along the way, which are decisions that are subjective and not really part of the standard operating procedures, can affect the results negatively. So this is one example here. This was an antidepressant Paxil. It was studied for several main outcomes. It had a clinical trial. It didn't have any effect. But as part of the study, the people who designed the trial, they collected some additional readouts from each subject, and they said, oh, but look, we found an association between this antidepressant and some other secondary outcome for which the experiment wasn't even designed, but we found it, right? And so they started the trial, started marketing the drug, and eventually it was shown that it was just an artifact association in the data, and it was not at all effective for the secondary outcome. So what was wrong there? What was wrong is that the scientists switched their objective in the middle of the study against something that the study was not designed for. And therefore, they kind of followed some artificial associations or artifacts which were not really appropriate. So here's another one, also from the same blog. So here people studied women at peak and off-peak fertility cycle. And arguably kind of deciding when it's off and when it's at peak, it's not trivial. So what they were doing, they essentially kept reclassifying the women who is in which group, right? And they did it by, as we were saying, looking at the data, right? I'm looking, this should be in this group, right? Oh, no, this should be in that group, right? And so on. Well, then we find silly things like that women at peak fertility like to wear red and pink shorts, right? So you can show pretty much anything, right? So, and there are many, many examples, to this. And to the point that here is the Journal of Psychological Science, which has a paper which states that undisclosed flexibility in data collection and analysis allows presenting anything as significant. So this is what I mean when I'm being really careful. So I'm totally agreeing you need to look at your data. You really want to detect, flaws in your, data collection and all of that. But at the same time, it is really important to decide upfront how the data will be analyzed and stick with that, no matter how we dislike the outcome. It is really important because otherwise it is so easy to be influenced by some random thing that we see, and we can really direct our follow-up investigations in a completely wrong direction. And as I say, at best, it will be a waste of resources. Okay, so this is to finish with that. So there are many ways to go in different directions. We're kind of trying to stay on tracks with that. So I will finish here. We have a 30-minute break, but if you have questions, I can. And then we come back here again at 3:30 for more hour.